So we're going to go through some examples of your indefinite integral notation, okay? And problems that you can see, x to the 1/2 dx. Okay, now remember, what this really might look like to you is they'll give you the square root function, and they want you to find the antiderivative of the function here. So, okay. So as you guys can see here, we're going to use here, what property do we use here with this? We're going to use that power rule. Is that right? So if you guys don't remember the power rule, x to the n dx by power rule is x to the n plus 1 over that n plus 1 plus c, assuming that n plus 1 is never 0, which means n can't be -1. Okay, so remember, this is all your antiderivative information you guys already had. This is big F of x plus that c. Okay, so remember, by the power rule, what do you guys do here with this function here? We take what? How about if we do this? X to the 1/2 plus 1 over what? 1/2 plus 1 plus that c, if you guys remember. And this is all now just arithmetic. So we change this to 2 over 2, 2 over 2 here, and remember, what do you guys end up with? 1/2 plus 2/2 is really 3/2, right? So we get x to the 3/2 over 3/2, add your constant, and then remember here that you're dividing by a fraction. So that's equivalent to multiplying by the reciprocal, right? So that'll be 2/3 x to the 3/2 power plus c. And you are done here. However, if you're looking back at the book, remember what we talked about. You see this 3/2 power? How can we write that 3/2 power? Yeah, as a mixed number, 3/2 becomes really what? 1 plus what? 1/2. So let's go through these details because students sometimes need it. That's 2/3 now x to the 1 plus 1/2 plus that constant. I'm focusing on these powers here. And by properties of exponents, okay, from beginning algebra, this is really x times x to the 1/2. So if you're looking back at the book, you might see 2/3 x square root of x plus c. Here's what you guys will actually see as an answer. Now, either of these answers are fine. However, it is, it's really simplifying this radical. So I want you to go consider what we just did here, because x to the 3/2 power is really technically the square root of x cubed. And that radical needs to be simplified. And that radical, when simplified, is going to be, if you go through and you try to find the largest perfect square that goes into this, x cubed. If you go back to those courses where you simplified radicals, this is x times the square root of x. So that's exactly the same as what you see over here. So there's a shortcut, and here's a shortcut, just to kind of emphasize this. I can write 3/2 as a mixed number. I can write any improper fraction. This is writing it as a what? As a mixed number. And when you do that, combined with your properties of exponents from beginning algebra, this is x to that first power, and this is the 1/2 power. And so, ladies and gentlemen, you now have a way to simplify radicals as kind of a shortcut by just simply writing that improper fraction as a mixed number. So this is our first, kind of example of the product rule with our indefinite integrals. Okay, and I'm going to go through something like this. Let's say this is if we put a homework sheet up eventually, we'll say number 3. We'll have the sort of very similar question for you guys. And you might say, well, how does this change? How is this different? Well, down here, this is still going to be x to the 1/2. However, that now means we have to integrate x to the -1/2 dx. Because that x to the 1/2 is in your denominator now. Is that right? Okay. And so focus again on the power rule. Our power now is going to be, if we go back here, -1/2. So by the power rule now, let's do this here. We're going to get x to the -1/2 plus 1 over -1/2 plus 1 plus that c. So just do your arithmetic again, and remember that I got to change that whole number to a fraction with a denominator of 2, and you now end up with x to the +1/2 over 1/2 plus a constant, and that's going to be square root of x over that 1/2 plus a constant, which now means 2 square root of x plus the constant here. So here's my antiderivative in general. Okay, so we're using everything we already knew how to do in how to determine antiderivatives, but we're using this notation, this integral notation. This, again, is an indefinite integral. Okay, there's no limits here. And they will be, just not right now. We have to go through these problems here. So assuming we have a future homework set, and we will, I'll go through these questions as if they're odd. Let's go further and say, what if they give us something like this, x squared plus 5 dx. So remember, in terms of notation here, that some books will just write it this way, some books will put a parentheses. They're just trying to emphasize that you have a sum here. Okay? And you have a sum of two functions. So let's remember, we did have a property where you had the first function plus the second function. Okay, this is integral of a sum, and integral of a sum is actually sum of what? Sum of integrals. Okay, it's the same exact property before when we found antiderivatives. So this is what we'll be using. And so we can think of this here as x squared dx plus 5 dx. And so now you have two integrals, right? So when you have two integrals, what do you guys remember doing here with this? When there's two integrals, we're going to do these separate. So on the left, we're going to use what again? Power rule. And then on the right, we have to integrate a constant. So I want to kind of emphasize here the difference here. The integral of a constant now. So two things here to remember here. Power rule says we have, let's write this down, x to the 2 plus 1 over what? 2 plus 1 plus, what happens when you integrate this constant here? Do you guys remember? Yeah, let's write this over here. Let's note here. When we looked at this function here as, in this case it's g, it's the second function, okay? When we did this work in the past, you might have said, can I think of this as x to the 0, right? Because that's just 1. And that's my constant, so I need the antiderivative here by the power rule. So we say, okay, 0 plus 1 here, 0 plus 1. And yes, it's going to eventually be plus a constant here. And so we say, oh, is that just 5x plus c? And the answer is yes. So this is going to be, for the second antiderivative, just 5x. Now they both have constants here. So if we really went through every detail, and let's do that. This is plus the first constant, and then this is 5x plus the second constant, okay? We need to go through these details. So what you've done is you found antiderivatives for both of these functions, okay? The integral of a sum is actually sum of integrals. So let's go back. We found this antiderivative. We found this antiderivative. Okay? Oh, we didn't finish this. Let's finish this. What is this? 1/3 x cubed plus c1 plus 5x plus c2. So I want to emphasize that this is my first antiderivative, and then this is my what? Second antiderivative. But then the question becomes, what do you do with the constants? Right? C1 and C2, these are both constants. C1 is the constant for the first antiderivative, C2 is the constant for the second antiderivative. So I want to remark to you guys right here. Look at those constants. If you ever add two constants together, and you will, C1 and C2, you could just call that C here. Okay, so let's write this down here. These two, this sum, can be replaced with just a constant C. So you may see in a lot of textbooks at the end, they write this answer as 1/3 x to the third plus 5x plus that constant C. And there's no subscripts for your constants now. So there's various ways to answer this kind of question. Some books will put constant C for the first one. Some books will put constant D and then a constant E. You know, they go crazy with the constants here. But if you know they're just constants, any constant plus a constant, which really means number plus number, is just number. So this is how we integrate here with the, integral of a sum. Okay? And we're using this notation now. We already know how to find antiderivatives. So if this was a worksheet in the future, we'd be at 7, because you guys know I only do the odd numbers. So we can give you another question here. And this time we can say, what if they give you x to the fourth minus 7? This is an illustration of the difference property. Meaning, again, if you have a function minus another function, and you're supposed to integrate, the integral of a difference is called difference of integrals. So I have f of x dx minus the integral of gx dx. Okay? So this is what we're going to use as well. So by this property, I have to integrate x to the fourth minus the integral of 7 again, of the constant. And let's actually use another property and write this down as a property here as well, so you guys can use this. If you ever have to integrate a constant, okay, and that shows up a lot, what is this going to be? You're going to just see cx plus, and again, we're in that weird situation, plus a constant. And both these c's are constants. But a lowercase c is a different constant, possibly, than the uppercase c. You guys know what I'm talking about? So this first constant is right here. And then you have a second constant out here. That's the part of your general solution. So that's going to be a nice property that we use here, because when I integrate this, we know that's 7x plus c2. Is that right? Okay, you guys okay with that? Good. We just have to integrate x to the fourth now. Now, this first integral is going to be x to the 4 plus 1 over 4 plus 1 plus that c1. So if we do the work down here, we get 1/5 x to the fifth, because 4 plus 1 is 5, right? Plus c1 minus 7x. Now I'm going to do something here that's really technical. Students really start to ask these kind of questions here. Right? Because you are actually subtracting a sum, and you are going to have to distribute here. So you end up with 1/5 x to the fifth plus c1 minus 7x minus c2. So people will ask again, like before over here, right? We have two constants again. Here are the constants. We got c1 minus c2. So when you take a first constant and you subtract a second constant, the answer again is just simply going to be a what? It's a constant. Okay, so this will be, let's write this down, this detail. C1 minus C2. You see this? You're just going to call that C for constant. So your final answer, ladies and gentlemen, will be 1/5 x to the 5th minus 7x plus that constant. There it is. Okay, so this is 7. You guys okay with that one? Right? And then number 9, if they give you something like this, they can give you pi cosine x dx. And so what I want to point out to you, there's going to be a couple of things you want to know here. You guys know anything about pi? What's interesting about pi? It's a constant. Okay, pi is a constant. It's about 3.14 approximately, 3.14156 approximately. It's approximately 22/7 as a fraction. It's actually an irrational number. Okay, the decimals never end, and there's no pattern to the decimals that you see there, decimal values. It's non-repeating and non-terminating, pi. So, but it's a constant. It's an irrational number. So the properties that we have written down that we're going to use here, remember, if you ever have to integrate a constant times a function, you get to pull out the constant and integrate the function. Okay? In other words, just pull out your c here. So if c is here, it's outside. So in this example, this is going to be pi times the integral of cosine dx. Now you're at a very, very important place here with these here. Okay, to let you guys know, this is kind of an important thing, that in addition to your properties of antiderivatives that we're now using with our indefinite integral notation, right? Remember last time we did all the antiderivatives, the properties, you're going to need to know these as well. Here's what I'm talking about. Last time we gave you a whole list and we talked about where it came from. You're going to need to remember and know this like you know your name. What's the antiderivative of cosine? Remember, you think of it this way. The derivative of sine is what? Cosine. So this is backwards. So we looked at this last time. If you guys remember, we said, okay, the derivative of sine here was what? Cosine. Remember that? Here's my antiderivative function. Is that true? And we called this last time, this is f. So if this is the integral of f, I need again the what? Antiderivative function, but add your constant. So it's back here, meaning this will be sine plus c, because this is what it was last time. Okay, so here's the thing about it. You want to know this like you know your name. This is only one of the trig functions. So if you remember here, we're going to go through these details. What was the antiderivative of sine? Do you guys remember that? Minus what? Minus cosine. So this weekend, you guys want to know this. And again, if you want to verify what we went through, all the details, as I said, if we went through that, if we differentiate minus cosine, right? Pull out the constant. What's the derivative of cosine? Anybody remember? What's your derivative of cosine? Is that minus sine? So that's minus sine, so we got what? Sine. So if this here is the antiderivative function, and this was that original function, right? They give us this f again. Here's my antiderivative. This is where it comes from. Okay, so we did these things last time with the antiderivatives, and again, that brought us to the next one. We can't integrate tangent, not in this class. Remember what we did last time. Just recall, because it's happening all over again. If I differentiate now the tangent function, what do I get? What's the derivative of tangent? Secant squared. So this is my antiderivative. This is my function. So we're going to say now, if I integrate secant, what's the antiderivative? Tangent. And don't forget to add your what? Constants. So this is the stuff that we worked on last time. Do you guys remember? So these properties here are going to be what you guys use forever. And yes, verify that this is happening. This is the antiderivative function, f, from last time. And here's our function that they gave us, little f. So these properties are happening. Let's see if you guys remember here. What about this property here? What's the antiderivative? Let's do this here again. Let's remember, I think we differentiated what? Secant, is that right? What's the derivative of secant? Secant tangent. So what that means is I can integrate secant tangent, and it's going to be simply what? Secant plus c. Because antiderivative function, that goes right here. This is the function they gave us. This satisfies the definition. So this is what we get with secant. So far we have 1, 2, 3, 4 trig functions that we have to remember. And then I think I gave you guys, what did we give you guys last time so you remember here? What's the derivative of cosecant squared? See if you remember. We can take the, I'm sorry, let me rephrase that. What's the antiderivative of cosecant squared? Anybody remember? Negative what? Cotangent. Yes, so let's write this down. Again, do you have to know this like you know your name? Absolutely. And when? This weekend. Because next weekend we'll do more work with this, or next week. So I just want to remind you guys, here's how we showed you how to do these here, right? If I differentiate minus cotangent, pull out the negative sign and differentiate cotangent. Right? What was the derivative of cotangent? Minus what? Minus cosecant squared. Minus the minus makes that a what? Plus. Okay, so it's back. So antiderivative function, they switch places here. Antiderivative and what? Function up here. Okay, so this is kind of, and what was the last one? Let's see if you guys remember the last one here. Anybody remember the last one? It's related to, see all of these up here. They're very similar. We forgot a dx here. Okay, we forgot a dx here. Oh, we've been forgetting our dx. Not good. Coffee's not even kicking in. Okay. What's the last one? Remember this one? Cosecant, cotangent. Let's put the dx. What was this? Is that minus cosecant? Okay. So remember, what was the details here? If we differentiated minus cosecant, pull out the negative sign, pull out the constant, derivative of cosecant, if you remember, negative what? That negative, first negative sign is there. Negative cosecant what? Cotangent, which is negative times a negative, which is cosecant cotangent. Okay, so here's my antiderivative. Here's my function. They switch positions. So this is the 6 trig integrals that you guys have to know like you know your name. Okay, so I want to go back and highlight these. So here's 1, here's 2, here's 3, 4, 5, and what? 6. So you know those 6. You also know the power rule. Probably the first one we did. Yeah. It's power rule here. And you know your properties. Okay? So this is going to be, like I said, what we do for the rest of the course. So let's even finish this question. Because we're at number, 9 here. So I have to find, really, what's the integral of cosine? Is that sine? Don't forget plus c. Now let's put all this together so you guys know. I'm going to put this together here so we talk about the details. That's pi now times what? Sine plus c, and again, you're going to have to distribute. Okay? So what do you guys get when you distribute? We're going to put it all the way down here. You get what? Pi sine x plus pi c. Now, pay attention to what happened here. Pi is a constant, is that right? C is a constant too. So since pi is a constant, c is a constant, when you multiply two constants, what do you get? Another constant. So I would say when I first took this course, I was pretty OCD, I guess. I didn't like putting down C again. In fact, what I used to do is I used to put this here as D for another constant. Okay? And so I used to change that letter to D because I didn't want to use constant C. I had this issue where I felt, well, it's a different constant. And the truth is, it is a different constant. It's a different number. So I called it a different letter. So the logic is there. And so you can put a D if you wanted and understand that to simply be constant. That's fine. But after looking at answers in your book, 20 answers, 30, 40, 50 problems, and I looked at all the answers, what do you see in the back of the book? They always put what? They put that C for constant. And so it's up to you. Okay, I understand if you put D, because I used to do that, or you start changing these letters, but you will grow just like me, just like I did, to eventually just put the constant C. It is a different C, but the point is it's just simply meaning that it's a constant. And you're done. So this is going over really every property that we've seen here. However, as we continue, let's go to another odd number, like number 11 here. They can give you the integral of, they can give you just a nice polynomial function, like 3x squared minus 2x plus 5. So here's just a nice polynomial now. What you want to do is use the properties. So I'm going to write that down here for us. Use the properties of antiderivatives or indefinite integrals. Okay, so here's how I kind of look at it. I first of all notice constant. Let's get the right. Constant, what is that? Constant, what is that? I see all my constants. So that stands out. So I'm going to say, okay, that's 3 times the integral of x squared dx minus 2 times the integral of x dx plus the integral of 5 what? Dx. So notice what stands out to me is all the constants. There you go. And then what also stands out is I got sums and differences. So I have a difference here. I have a sum. I wrote this here as a difference. So this is what stands out. And so finally now, if you notice, all I need to do is find here an antiderivative, antiderivative, and really altogether, I could do this one here. Let's do this here. I can pull out my constant so you guys know. I can write this here by pulling out the 5. I can integrate dx. So I'm going to have a constant, and yet I still have to find that last what? Integral, dx. So this is visually what I see happening here, okay? It just stands out to me, all the properties here. And then, what do we do here? In gray, we need all those antiderivatives, right? So I have 3 now. What's this? Can you guys do these in your head now after last week, or last time and this time? So what do I write down? What's 2 plus 1? X to the third over 3. You use the power rule. Minus 2 times, what's this one? X squared over 2. Take the 1 power, add 1, and it's 2. Then divide by the same number. And this is plus 5 what? X. Okay, because this integral here is x. Oops. This integral here was 1/2 x squared, right? And this is 1/3 x cubed. So you start to do this in your head, and don't forget you have to add your what? Constant c. So your final answer will be x cubed minus x squared plus 5x plus the constant c. So you'll get really good at identifying these properties here, you know, separating, pulling out your constants, writing your integrals of sums as sums of integrals, integrals of difference as difference of integrals. And, you know, you can put that constant at the very end. You don't have to put the c's everywhere. I used to do that. Just leave your constant at the end. And then they're going to kind of trick you here and say we're going to give you x, 1 minus the square root of x dx. And you might say, why are they going to trick us with this one? Anybody remember last time when you guys did these here? Yeah, you guys remember last time? Let's put it down there so we can see it, I guess. Is there a property that is the integral of a product? Is there a product property? Say what? No. In other words, here's what I mean by that. The integral of a product here of 2 functions, ladies and gentlemen, what I mean, there is no, this does not exist here. And that's something that students do a lot of. So don't do that. What do they really want you to do here? Do you guys know? Distribute. Yep, distribute. So you get the integral of x minus x square root of x dx by the distributive property. But that's really going to be the integral of x, and put that in parentheses, minus x to the 3/2 power dx. Okay, you guys okay with that one? So why is that x to the 3/2? Properties of exponents. Is that right? X to the first power times x to the 1/2. 1 plus 1/2 is really what? 3/2. Is that true? Okay. So now use your properties. You say, what are my properties here? The integral of x dx minus the integral of x to the 3/2 dx. What is each integral? What's this? 1/2 x squared. What's this? Well, I guess that's a little bit more work. 3/2 plus 1 over what? 3/2 plus 1. Don't forget to add your constant, right? So I get 1/2 x squared minus, if you want to see every detail, x to the 5/2 over what? 5/2, yes, plus a constant. Don't forget that, what's 3/2 plus 1? Right? You guys know what that is? That's 5/2, right? Got to change the color, I guess. 2 over 2. 2 over 2. Okay, so you get that 5/2. Now, technically, yes, you distribute. Okay, so you're going to get 1/2 x squared minus, this is 2/5. This is a reciprocal. Is that true? You guys understand here what we just did? Down here, if you divide by a fraction, right? Do you guys remember? You're multiplying by the reciprocal. Okay, here's, if you got to see that detail, some people may have to. Remember this? This is divided by what? 5/2. You multiply, this is what we're saying, by the reciprocal of the second fraction, the one on the right. So that's why that constant is now a product up there, and it's reciprocated. So anyway, that's there. Let me point out another detail. You also see what here? Minus c. So here's another detail for you. We can write this as plus a minus c. Okay? Because if you're looking back at the book, here's your final answer. You'll see 1/2 x squared minus 2/5 x to the 5/2 plus a c. And that confuses students. They don't know why is it plus c when I distributed and got a minus c? Well, because you put plus another constant right here. You see that? You put plus a negative constant, and maybe you called that constant another letter, plus d. So this is really plus a constant, okay? And you said, oh, can I write this down here as plus d? And I'll say, yes, you can. That's perfectly fine. But after you see a million of these examples, you notice in back of the book, they always just put a what? Plus a c. So this is why, ladies and gentlemen, in back of the book, they put plus c. Now, what else you guys notice here? I want you to point something out. 5/2. How do you simplify this? Remember what we talked about? Yeah, you write 5/2 as a what? As a mixed number. What is 5/2 as a mixed number? It's 2 and 1/2, I think. Is that true? But 2 and 1/2, by definition, is really 2 plus 1/2. So let's see what this means again. 1/2 x squared minus 2/5 x squared square root of x plus not d, but plus what? Plus c. So this is exactly what you'd see in back of that book, going through every tedious detail. And it's helpful because when you go through and you do homework, you don't want to look back there and you go, I have a plus c, I got a minus c, I'm not doing my homework anymore because I don't know what's happening. How do they write x to the 5/2 as just simply x squared square root of x? Well, because for that simplification we told you guys, right? Right? X squared plus 1/2 is really x squared times x to the 1/2. And that's x squared times the square root of x. That's where that came from. So here's every detail. And these are questions you guys can see, right? Let's kind of go further and do some more. Integral of square root of 2 over x dx. Or let's change this. Let's do this here. Yeah, no, we can do it that way. That's fine. I apologize. Okay, and here I want to show you guys another thing that's happening here. I want you to recall just some algebra. If you have the square root of a what? Of a quotient. That's quotient of square roots. Is that right? So what this happens here, what this means is I got the square root of 2 over what? Square root of x dx. So this question is the same. Now, notice here you have a constant. So pull out your what? Constant. Okay? And then notice what you have down here. That's the square root of x. And you say, well, how do I write the square root of x? That's x to the 1/2. And it's in the denominator. So we really have the square root of 2 times x to the minus 1/2 what dx, right? Okay, you guys okay with that one? That's what we have. So now we just have to integrate, find the antiderivative of this function here. Okay, and again, what rule do you use to do that? Anybody know? Minus 1/2 plus 1 over minus 1/2 plus 1 plus c. You use the power rule. Is that right? We're trying to find that integral. What's minus 1/2 plus 1? Well, it's minus 1/2 plus 2/2. So your final answer here is going to be now, or we're going to have by the power rule, what's negative 1/2 plus 2/2? Is that 1/2? You're dividing by 1/2 plus that c. So what does this mean? 2 square root of 2, square root of x, plus c. Here's your what? Final answer. So don't let that fool you, because they can give that to you. Okay, and if you guys remember a little bit of algebra, they can even give you like the cube root maybe of what? Let's say 5x squared dx. They may have you do a little bit of algebra. Okay, so let's remember something here. Let's recall. When you have radicals, like a cube root, or I should say just in general, an nth root. What's the nth root of a product? Isn't that the product of nth roots? I could have done the same thing up here, but they gave me the square root in particular. So in this example, we can say that the cube root of what? Of a product is product of cube roots. So my integral is really going to be the cube root of what? 5 times the cube root of x squared dx. And don't forget, the cube root of 5 is a what? That's a constant. Good. So we pull that out. Cube root of 5, that's the constant, times x to the, what power do I use here? Yeah, that's going to be 2 over 3, right? Okay, so I want to point this out here. A couple of things happening. The cube root of x squared is really x to the, what, 2/3 power. And your constant here is outside now. Okay, so if you want to remember, how do they write that? I guess they put this as m x to the n, and that's going to be equal to x to the n over m. This is what we used here. So now I just simply use to integrate I have to do this integration. I have to use there the what? The power rule. Okay? So we'll get, let's put this here now. Let's do this integration now here. 3 square root of 5 now times x to the 2/3 plus 1 over 2/3 plus 1. Yes, you got plus a c if you want to do it that way. Or if you guys know you're going to distribute at the end anyway, we could just simply say, hey, plus c out here at the end. So we have some arithmetic, right? We're going to have to add these powers here. And what's 2/3 here plus 3/3, because 1 is really 3/3, right? Yeah, you're going to have 3 square root of 5 x to the what power? Oops, x to the what, 5/3? Over 5/3 plus c. 3 square root of 5 times 3 over 5, x to the 5/3 plus that c, which we really get 9 square root of 5 over 5. And then notice again, we're going to have to write this as a what? My 5/3 is written how? Isn't that 1 and 2/3, which is 1 plus 2/3? Is that true? You guys with me on that? So if you're looking back at the book, you might say, I see x here, and yes, that's x to the 2/3 plus c. They're not going to write it that way. How do they write it? Do you guys know? Cube root of what? X squared plus c. Okay, because they really simplified this radical over here. Right? You got x to the 5/3. That radical is simplified. Oops.
Where did that 9 come from?
Excuse me?
Where did the 9 come from?
Where did the 9? Oh, the 9 came from right here. See this up here?
But where did that 3 come from then?
Where did the 3 come from? See this over here? You see the sum down here? 2/3 plus 5/3? Or 2/3 plus 3/3 is 5/3, right? So down here, here's the question. Where did this... Well, here's what I'll go back and take a look at. There's a 5/3 here. Is that true?
Where?
Isn't there 5/3? Because this power now is 5/3. Is that true? Mm-hmm. There was already a 3 out here. So what you have to do is write this. You have division of 5/3. You have to write it as a product of 3/5.
But that 3 wasn't a part of, it's the cube root of 5.
And, oops, very bad. Thank you so much. Thank you for being awake. That's not a 3. Good job. Sorry about that. Oh my God. Maybe we should erase this one. It's not a 3. That's what? Good job. Cube root of what? 5. Good. Good. This is going to be a what? Cube root of what? 5. Okay. Let's go back now. Thank you so much. Let's change this. Here we go. 3/5 cube root of what? 5. Plus that. So you can write this as 3 cube root of 5 over 5 plus your, don't forget there's an x there. Cube root of x, this is a cube root. Yeah, be very careful. I apologize. Good, very good. So do we have time for another one, or do you want to, what do you guys think? How about this? Should we have time for another question? What do you guys think? Yeah, okay, let's do this here. Okay, let's go over some more of these here. I'm going to say this is 19. And we're going to integrate 3x plus 2 times x minus 5 dx. Okay, so what I want to remark here about this is that there is no such thing here as a product rule for integration. And so what you're going to have to do here is you're going to have to use FOIL here. So you're going to use your FOIL technique, multiply your first terms together, your outer terms together, your inner terms, and your last terms. So you'll end up here with, let's double check. Yeah. By doing that algebra, we get 3x squared, first terms, outer terms, minus 15x, inner 2x, minus 10. We combine our like terms, 3x squared minus 13x minus 10. So this is what we get here when we use FOIL. And now we're going to integrate. We have 3x squared minus 13x minus 10. So at this point, we're going to use properties of integrals. I'm going to point out to you again that we have constants here. -3, -13, -10, and we also have these operations here of subtraction and subtraction here. So by our properties, we'll get 3 x squared dx minus 13 x dx minus the integral of 10 dx. So if you actually wanted, we can actually go through this where, since we're learning this from the beginning, let's just focus on here the sums and differences. So here's the sums and differences here of these properties. But you're going to pull out your constants, the 3, the 13, and the 10. So you'll have 3 integral x squared dx minus 13 integral x dx minus 10, just the integral of dx. So I think we'll do it this way. I'm just going to pull out these, use the properties here first of your integration, sums and difference property, and then pull out your constants. So notice here you have your constants on the outside. And what we focused on was the sums and differences. In fact, specifically, there's differences. So we use the properties there. And now what we're going to have to do is for each one of these, we're going to have to integrate. So we're going to have to integrate each one. And we're going to use the power rule here. So this integral becomes 1/3 x cubed. This integral becomes 1/2 x squared, and this is just x. And we use power rule for each one of these. So altogether now, you'll have 3 times 1/3 x cubed minus 13 times 1/2 x squared minus 10x plus that constant c. So 3 times 1/3 is just going to be 1, so I get my x cubed minus 13 halves x squared minus 10x plus c. And there you go. So what I want to remark here is there is no product rule. So never do the following. There's no such thing as f of x gx dx being simply the product of two integrals. Do never do this. This is not equal. They're not the same. So you have no choice but to use the algebra here. So if we go to number 21, so 21, this integral is going to be 2x cubed minus 1 over x squared dx. And I want to remark that under this radical here, or sorry, not your radical, okay, you really have 2x cubed minus x to the minus 2 power here. So this integral here is now going to be 2x cubed minus x to the minus 2 power dx. So I have a difference of integrals here. The integral of a difference is difference of integrals. 2x cubed dx minus x to the minus 2 dx. So here's my difference property. I have only one constant to pull out. So we'll have 2 integral x cubed dx minus that integral of x to the minus 2 dx. So at this point, again, I have 2 integrals to perform using the power rule. So by the power rule here, let's find out what these integrals are. Remember, the power rule is going to add 1 to the power. So I'll have 1/4 x to the 4th. Because I add 1 to the 3 and I get 4 and I divide by the new power. Now when I add 1 here to the negative 2, don't forget there's already a subtraction sign there. I get x to the negative 1 power over negative 1 by the power rule. So maybe we should look at the details if people feel they need to see that. X to the 3 plus 1 over 3 plus 1. And this one is going to be, let's do it this way, x to the negative 2 plus 1 over negative 2 plus 1. This is the power rule. And don't forget, ultimately, we're going to add that constant c out here, but let's see what we get. Remember, we pulled out this power, constant, 2 times x to the 4th power over 4. This is minus again, right here. X to the minus 1st power over negative 1 plus my constant. So I'll end up with 1/2 x to the 4th plus 1 over x plus that c. Because over here, minus a minus makes this a plus. And the definition of x to the minus 1/2 here is 1 over x. So we're done. This is number 21. We're going to integrate 3x plus 7 over the square root of x. Now what you have here is a quotient, but we don't have a quotient rule for integration. So what you're going to need to do here is you're going to have to use some algebra. And by the algebra, we're going to have to distribute your division by the square root of x. And so we're going to use some properties of exponents, meaning you get 3x to the 1st power over x to the 1/2 plus 7 over x to the 1/2. So by properties of exponents, we have 3x to the 1 minus 1/2 plus 7x to the minus 1/2. So this gives us 3x to the, don't forget how to subtract fractions. So this will be 2 minus 1, which is 1. This is plus 7x to the minus 1/2. Now this is what we're going to integrate. We're going to integrate 3x to the 1/2 plus 7x to the minus 1/2 dx. So we had to do all this algebra before we actually start to use our properties and power rule for integration. And so now, let's use the properties. That's a sum. So we have 3x to the 1/2 dx plus 7x to the minus 1/2 dx. Constants here to pull out, a 3 and a 7. 3 x to the 1/2 dx plus 7 x to the minus 1/2 dx. So notice I pulled out my constants. What we're going to use now here is power rule to perform our integration. So this integral here will be x to the 1/2 plus 1 over 1/2 plus 1. This is going to be x to the minus 1/2 plus 1 over negative 1/2 plus 1. And don't forget again how to add fractions. So here's what we're going to end up with. This is x to the 3/2 divided by 3/2, and this is x to the 1/2 divided by 1/2. And don't forget, all along, we had the addition here. And don't forget your constants. So let's put this all together. But maybe before we do, let's notate. This 3/2, this 1/2, we're dividing by a fraction. So that means we have 2/3 x to the 3/2 plus 2/1 x to the 1/2, because if you want to look at the detail again, this is x to the 3/2 divided by 3/2, which was x to the 3/2 times 2/3. And the same thing is happening for the other term there, right? We're going to divide by here 1/2 here. So we put divided by 1/2, which is x to the 1/2 times 2/1, and this is how we got what we got. So, okay. Let's not forget our constants here. So we need to change this. Here we go. We're going to bring down the 3. We get 3 times 2/3 x to the 3/2 plus, bring down the 7. 7 times 2 x to the 1/2, and don't forget to add your constant. So my 3's will cancel. I get 2x to the 3/2 plus 14x to the 1/2 plus that c. Now remember here, what you have by definition, x to the 3/2 will be the square root of x cubed. Now that's a radical that can be simplified. So my recommendation is to look at that power of 3/2 and write that as a mixed number, which is 1 and 1/2. And so you're going to get, like we've seen already, we'll say 2x to the 1 times x to the 1/2 plus 14x to the 1/2 plus that c. So this ends up with 2x square root of x plus 14 square root of x plus your constant. So we've seen this before, where if you go back and focus on this 1 and 1/2, remember that's the same as 1 plus 1/2. This is why you have a 1 and a 1/2 here. Anyway, this is number 23. Number 25. 1 plus x squared cubed dx. Now, you're going to again have no choice but to use algebra here. But this time we have to write down what that means. You have 1 plus x squared cubed, which means 1 plus x squared plus 1 plus x squared plus 1 plus x squared. You're going to have to use FOIL here. So for these two terms, the first two, we use FOIL. So we'll get 1 plus x squared plus x squared plus x to the 4th, and that will be multiplied to 1 plus x squared. When you simplify, you get 1 plus 2x squared plus x to the 4th, and that's multiplied to 1 plus x squared. So now you're going to multiply again. This is not FOIL, I call it FOIL-ish, because 1 gets multiplied to every one of these terms, and x squared gets multiplied to every one of these terms. So we're going to multiply again. So let's do that. We get 1 plus 2x squared plus x to the 4th when we multiply 1 with every term. And notice what I'm going to do. I'm going to put when I multiply x squared to every term on the left, I'm going to put it under the appropriate place here. X squared plus, this will be 2x to the 4th plus x to the 6th power. So I'll get 1 plus 3x squared plus 3x to the 4th plus x to the 6th power. So this is what I'm going to have to integrate. So we're going to have to do all this algebra first. Make sure that you raise this to the third power, because that's what you have. You have an exponential. Okay, and this over here is your base, so you know that. So you're going to raise that to the third power. So now we're going to use properties here of integrals. I have sums. So the integral of a sum is sum of integrals. And so we'll write that down that way. Dx plus 3x squared dx plus the x to the fourth dx plus x to the sixth dx. And now I get to pull out all my constants. Wherever I have a constant, I only have 2. So we integrate dx plus 3 x squared plus 3 x to the fourth plus the integral of x to the sixth dx. So make sure that the constants are out. And now we're going to perform our integration here, because we have actually 1, 2, 3, 4 integrals to perform. And don't forget that the properties here of addition, we're going to add all those answers together. So we're just using our properties, and now we get to integrate. And we're going to integrate by the power rule. We know this integral is actually just x. We know this integral will be, by now, hopefully, 1/3 x cubed. This will be 1/4, sorry. This will be 1/5 x to the fifth. Because when I add 1 to the power 4, I get 5. This is the 5 we're talking about right here. I just divide by that new power 5. Like for the prior integral, 2 plus 1 is 3. We're looking here. This is why our power is 3, and we divide by 3. In this next question here, we got the power 6. So by the power rule, this is going to give us x to the 7th, because 6 plus 1 is 7. And we divide by 7. So this is called the power rule. And then don't forget to add your constant at the very end. But we have to put everything together here. X plus 3 times 1/3 x cubed plus 3 times, or 3 over 5, x to the fifth plus 1/7 x to the 7th plus our constant. So our final answer will be x plus x cubed plus 3/5 x to the fifth plus 1/7 x to the 7th plus your constant c. Because 3 over 3 cancels here, and that's why there's a 1 there. So this is how we integrate after we did all the algebra. And this is question number 25 from our worksheet. 27. Here's what we have. We have 3 plus the cube root of x squared dx. So we have some algebra to use here. So let's write that down. Now remember, your power here is 2. So that means we have 3 plus the cube root of x times another 3 plus the cube root of x. So by FOIL, we end up with first terms, 3 times 3, which is 9. Outer terms, 3 cube root of x. Inner term, 3 cube root of x. And the last term, well, that's going to be the cube root of x now to the second power. So let's remember what this would be. X to the 1/3 to the second power means we have x to the 2/3 because what we do here is we multiply our powers. 1/3 times 2 is actually 2/3. This is how we get that 2/3. So combining like terms here, we get 9 plus 6 cube root of x plus x to the 2/3 power. And we can also replace this with x to the 1/3 so that when we integrate, it'll be already in a form we could use. So this is what we do here. This is how we use FOIL. So we had to do this algebra here before we can actually get a function to integrate, and it has rational exponents here. Okay, by the properties now. Addition, addition. So the integral of a sum is sum of integrals. Here's that sum. And then we pull out our constants, wherever there's a constant. So here's our constants, 9 and 6. So what's left is to integrate here, here, and here. Don't forget we have our sums here. So we're now going to integrate. We get x. Now we're going to use the power rule here. X to the 1/3 plus 1 over 1/3 plus 1. X to the 2/3 plus 1 over 2/3 plus 1. So remember that 1 could be replaced with 3/3 here in both cases so that we can add. Okay, so this is going to give us x to the 4/3 divided by 4/3, x to the 5/3 divided by 5/3. And you know that when you divide by a fraction, this 4/3 here, let's do this, 4/3 and 5/3, you end up simply multiplying by the reciprocal. So it's 3/4 x to the 4/3, 3/5 x to the 5/3. So let's put this all together. We get 9x plus 6 times 3/4 x to the 4/3 plus 3/5 x to the 5/3 plus our constant c. And so we have to simplify our fractions here, or in one case, this is 3/2 here. So we'll end up here with 9x plus 9/2 x to the 4/3 plus 3/5 x to the 5/3 plus c. So notice again your powers here are fractions and they are improper. And I'm going to say or suggest, because when you write these as radicals as a final answer, I mean, you could give this as an answer, that would be fine. But if you're looking back at the book, you might see radicals instead. And so these radicals have to be simplified. So write this as a mixed number. 4/3 is really 1 and 1/3. 5/3 is 1 and 2/3. So when you write this as a radical now, this will become 9x plus 9/2 x times the cube root of x plus 3/5 x times the cube root of x squared plus the constant. because we wrote these exponentials with rational exponents in terms of radicals, or I should say as radicals. And there you go. Number 29. X to the fifth plus 2 minus 1 over x to the eighth dx. So we're going to use our properties. Integral of a sum is sum of integrals. Integral of a difference is difference of integrals. So you're going to have x to the fifth dx plus the integral of 2 dx minus 1 over x to the eighth dx. This is using our sum and difference properties. Pull out your constants. And in this case, there's only one. And remember, 1 over x to the eighth, if we're going to use the power rule, and we are, we have to write this as x to the minus eighth power. So we have actually used all our properties, sums and difference, and pulled out our constant. And we wrote 1 over x to the eighth as x to the minus 8. So now we get to integrate. We have 3, and we're going to use the power rule. So don't forget, for the middle integral, that's really x to the first power. So let's do power rule here. This becomes x to the 5 plus 1 over 5 plus 1, x to the 1 plus 1 over 1 plus 1, x to the negative 8 plus 1 over negative 8 plus 1. So we get x to the 6 over 6, x squared over 2, x to the minus 7 over minus 7. So let's start to put all this together. 1/6 x to the 6 plus 2 times x squared over 2, because there was already a 2 here, minus, we should say, x to the minus 7 over negative 7, and don't forget to add your constant. So we can simplify a little bit here and say this is 1/6 x to the 6 plus x to the second power, minus the minus makes this a plus, 1 over x to the 7th power, because x to the minus 7th power is 1 over x to the 7th, and add your constant. And you're done. This is 29. We have the integral of 6 cosine x plus 2 sine x dx. So again, we have an integral of a sum, which is sum of integrals. So I'll say 6 cosine x dx plus the integral of 2 sine x dx. So we used our integral of a sum as sum of integral property. Let's pull out the constants. So the constants are out. So what this means now is that I have to integrate sine and cosine. So we need the integral of cosine, the integral of sine, or we should say the antiderivative of cosine and the antiderivative of sine. Let's see. The derivative of sine is cosine, so the antiderivative of cosine is actually sine here. The derivative of cosine is minus sine, so the antiderivative of sine is minus cosine. So let's put this together. 6 sine, positive 2 times a negative is minus 2 cosine x plus that c. And you're done. $33. We have the integral of 1 plus cosine squared theta over cosine squared theta, and now you have d theta. So what I want to remark here is it doesn't matter if your variable is x or theta. We're going to integrate here with respect to d theta. So this is a change of variables. It's okay, it's fine. It works exactly the same way. Now, I want to remark again that you do not have a property that says the integral of a quotient is not quotient of integrals. That's not true. So you can't do this. But as you've seen is we're going to have to use some algebra here. So this is what I mean by using algebra. This cosine squared is dividing both terms. It's dividing a sum. So make sure your cosine squared theta divides both terms. So we got to use the algebra so we can simplify. And so 1 over cosine squared theta is actually secant squared theta. Cosine squared theta over cosine squared theta, anything divided by itself is 1. So what you're seeing here is that we have to integrate secant squared theta plus 1 with respect to theta. That's why we put the d theta. So now we can say the integral of a sum again, here's your sum, is sum of integrals. So I use my property. There is a summation property, there is a difference. There's just no quotient or product property of integrals. So at this point, we're going to have to integrate secant squared theta and just d theta. So the d theta is pretty simple to do. That's theta, and don't forget to add your constant c. Now we need to know what the integral of secant squared theta was. Now remember, we talked about this earlier, that when we differentiate tangent, we get secant squared theta. So the antiderivative of secant squared theta is actually tangent theta. So putting this together, tangent theta plus c is our final answer. So we're going to have to remember for some trig functions, some algebra and some properties, I should say, are some identities with our trig function. And the reciprocal of cosine is actually secant, and so we actually use that property right here. That's why we got secant squared. So we use our reciprocal identity, and you're going to see some of these in other questions. Like 35. Integral 2 pi sine theta, sorry, not sine theta, we have secant theta tangent theta. And you don't have to use a property here, but at least not a trig identity property. We are going to use an integral property because we have a constant times a function, so we have to pull out our constant. So we pulled out the constant. So we did use a property of integration, but there is not going to be a property here for a trig. You're not going to use a trig identity because you know already that if we differentiate secant, we get secant tangent. See, at this point, we have to integrate. We have to integrate that secant tangent. Derivative of secant is secant tangent. So the antiderivative of secant tangent is actually secant. So we can write this down. So that's secant theta. And don't forget to add your c. But when you bring everything down here, you say, is this 2 pi times secant theta plus c? The answer is yes. We'll go through the details. Yes, you multiply. I should say we distribute. And you'll get 2 pi c. And like we mentioned earlier, 2 pi c is just another constant. So you can call that constant d if you like. Or some books simply call it again c. And that's another c. In fact, all books call it that. Because 2 pi times a constant is just a constant. So your final answer is 2 pi secant theta plus that constant. So I'll just remind you of this detail because it does show up. And it's not that big of a deal. Some people just put that constant at the very end. That's all. $37. 37, we have the integral of sine theta plus sine theta tangent squared theta, everything over secant squared theta. Now for this question, we're going to use some algebra here because we don't have a quotient rule for integration. So we got to use some algebra so we can simplify this rational, this quotient, and we notice that we have this secant squared theta dividing a sum, so that's what we're going to focus on. So we distribute the division. Sine theta over secant squared theta plus sine theta tangent squared theta over secant squared theta. And actually, in all honesty, I think I see another way to do this that might be better. We're still going to use algebra. I can still stick with this, but I won't for now. Here's what I want to point out to you. You notice that we have sine theta and sine theta. I'm going to factor that sine theta out. So I get sine theta 1 plus tangent squared theta. This is over secant squared theta. So all I did was factor out my sine theta, and I have 1 plus tangent squared theta. And then I'm going to point out another fact. That 1 plus tangent squared theta, we know what that is. That's a Pythagorean identity. This is secant squared theta. So sine theta times secant squared theta over secant squared theta, this is going to cancel because anything divided by itself is 1 or cancels. I'm just left with sine theta. So that was a little bit easier to handle than we originally approached this. And sometimes that happens. So what you're going to do here is use properties of identities from trigonometry to simplify your trig function here. And this problem was really all along just the integral of sine. This is what I'm saying. This whole problem here is just really the sine theta. That quotient is equal to sine theta. So now we have to use, or remember, what's the integral of sine theta? The derivative of cosine is actually minus sine, so the antiderivative of sine will be minus cosine, plus that constant. And you are done. So this concludes our exercise in what we've been doing here. These are these indefinite integrals here.